All right, welcome. Today we're diving into one of the most dynamic features of the Lamina Continuum. We're talking about its incredible ability to physically rebuild itself, all in the name of peak performance. So let's just start with a really fundamental question. When you think about what slows down high-performance computing, your mind probably jumps straight to processing speed, right? But in most really complex systems, the real culprit, it's something else entirely. Yep, you heard that right. It's not about how fast you can think, it's about how fast you can talk. In any complex system, doesn't matter if it's a silicon chip or a huge cognitive architecture, the cost of communication, just moving information from point A to point B, is a massive, massive barrier to efficiency. So, to really get how the Lamina Continuum cracks this problem, we're going to break it down. We'll look at those hidden costs, see how the system literally listens to itself, figure out its ideal state, and then get into the really cool part, how it physically rebuilds its own structure. Okay, so let's get right into it. Why is something that sounds so simple, just two modules talking to each other, so incredibly expensive? Well, this problem exists at every single scale you can imagine. Down at the hardware level, you're fighting the laws of physics. Moving these huge 64-bit numbers around a chip eats up silicon area, it burns energy, and it clogs up precious memory bandwidth. Then you go up to the software level, and every single time one module calls another, you're adding overhead, you're creating latency, and you can even destabilize the whole system. A system can't optimize what it can't measure. It's as simple as that. So its first job is to become a really, really good listener, tracking every single conversation happening between its functional modules. And it does this with something called the call frequency matrix, or CFM. Honestly, the best way to think about it is like a live traffic report for the entire system. It shows you exactly which modules are constantly chatting and which ones pretty much keep to themselves.
And look how simple and clear the output is. The system can see, just at a glance, that modules A and B are inseparable. They're always talking. Meanwhile, module C is off doing its own thing. This one simple piece of data is the key to absolutely everything that comes next.
Okay, so the system knows who's talking to whom. But what's the point? What's the goal here? Well, the ideal state it's always striving for is something called maximal functional cohesion. In plain English, cohesion just means that all the parts inside one module should be super tightly related and totally focused on solving the same problem. You don't want a module that's a jack of all trades, trying to do 10 different unrelated things. No, it needs a single, unified purpose. And this isn't just some vague idea. You can actually measure it. The cohesion ratio tells us if a module is self-sufficient, if its business is mostly internal, or if it's constantly having to make those expensive calls for outside help. The system's goal? Get that ratio as close to 1 as humanly or, well, as computationally possible for every single module. And this quote just brilliantly nails why cohesion is so critical. A module isn't just a folder for organizing your code. Not at all. It's a fundamental unit of stability. It's a container for learning and reinforcement. And most importantly, it's a self-contained unit for high-performance execution. Okay, this brings us to the main event. Now that the system knows who's talking and what its goal is, it can use that data to physically change its own architecture while it's running. This idea is called structural neuroplasticity. So who does this? This incredibly important job belongs to the structural governance layer, or SGL. Think of it as the master architect for the whole system. It's constantly watching that cohesion data from the CFM, and it has the authority to redraw the system's own blueprints on the fly. And the process is really straightforward. If the SGL sees two modules that are constantly calling each other, just like modules A and B from our traffic report, it triggers a merge. It physically fuses them into one brand new, highly cohesive module. Problem solved. And, of course, it works the other way too. If the SGL finds a single, bloated module that actually has low internal cohesion, meaning it's really two separate functions just jammed into one box, it'll find that fault line and trigger a split. It cleanly breaks it apart into two new, smaller, and way more focused modules. So, you might be asking, why go to all this trouble? Why is the system constantly rebuilding itself? Well, the payoff is a massive improvement in performance, all thanks to a concept known as execution locality. Execution locality is a really simple but incredibly powerful idea. It just means that when a piece of code runs, everything it could possibly need, all its data, all the other functions it has to call, is right there, physically in the same place. There's no need to make that slow, expensive trip across the system to go get something. And the benefits here are real and they're measurable. You get higher cache reuse, which is huge. It means the processor finds what it needs in its super fast local memory. You get way less cross-module dispatch, cutting down on all that wasteful overhead. It even leads to things like lower call entropy and more stable reinforcement learning. At the end of the day, you get a system that's just flat out more efficient and predictable, all because it was smart enough to minimize its own communication costs. So let's just take a step back and put this all together. What we've just walked through is a fundamental shift in how we think about software. We're moving away from a static blueprint and towards a living, adaptive architecture. The Lamina Continuum isn't just a block of static code, it's a living system. It has this beautiful, elegant loop. It observes its own communication, it analyzes itself for any inefficiency, and then it acts, rebuilding its own boundaries to become better. This observe, analyze, act cycle, that is structural neuroplasticity in action. And this leaves us with a really fascinating final thought. This kind of self-optimization, it's not just a clever engineering trick. It's a foundational step toward truly adaptive systems. So if an AI can learn to physically change its own structure just to be more efficient, what's next? What other structures, both inside and out, could it learn to change?